Welcome to this web lecture on the fixed charge transportation problem. So we've been seeing in past two web lectures what the transportation problem is and how to solve the transport problem using heuristics. In this lecture, we're going to slightly extend the fixed charge transport problem. But for that, let's quickly look into the instance again, into the example that we've been using. So we have the TOE bike sharing system, where you can rent a bike at one location and drop it off at another location on campus. The problem with this other location in this example is that it is possible that some locations all of a sudden have fewer bikes and some of them have more bikes just because of demand imbalances. So what the operator of such a bike sharing system has to do, they have to ensure that sufficient bikes are available in all buildings by moving bikes between buildings at as little cost as possible. So for instance, they're loading bikes onto a truck like here in this example picture, which is from a bike sharing system in Antwerp. So here we're now having two locations in the left, so Atlas and Gemini, which have more bikes than they actually need, and we have three locations on the right, which is the auditorium, which is Luna, and which is Vertigo, which have less bikes than they need. So they have a demand for bikes, and the demand for bikes is 8, 11, and 6, while the supply of bikes is 15 and 10. And then we have costs. So we have costs of 5 for moving one bike from Atlas to auditorium, for instance. So as we saw on the previous slide, these bikes are usually loaded onto a truck, which means that we don't only have variable costs, but we also have fixed costs for sending this truck. And these fixed costs are given by this value 12. So as soon as we move at least one bike from Atlas to auditorium, we incur a cost of 12. So we obviously don't want to reinvent the wheel, but now let's look into how we're modeling this. So we're looking into the recipe for formulations, identifying sets, parameters, introducing decision variables, formulating constraints, and the objective function. And from this point, we're going to use the transport problem as a template for our math model, and we're just going to extend that a little bit. So we have two different sets, which is our sources and sinks, or origins and destinations. So our sources are Atlas and Gemini. Our sinks are auditorium, Luna, and Vertigo. We have parameters, supply, demand, and transport costs. And of course, we have one additional parameter, which is the fixed cost. So for instance, the 12 for moving the truck from Atlas to auditorium. Our variables, in this case, used to be the number of bikes that we're transporting from I to J. But now we're, of course, also adding a second decision variable, which tells us if this arc from I to J is opened. So if we send a truck from Atlas to auditorium. If we're looking at the constraints, we still want to transport as many bikes as possible. We still want to receive sufficient bikes, and we still have non-negativity. Of course, we additionally also have to restrict the variable y. So we have to say y is either 0 or 1. And of course, y is also going to affect the objective function. So we have to add this term Fij plus Yij, overall I and j. Now, let's see, is this problem actually optimal? Or a different question, why is this the solution to this problem? So we're sending 11 vehicles from Atlas to Luna, but y remains 0. Why is this the case? What are we missing? And what are we missing? The answer to this question is we're missing a linking constraint. We don't have anything that tells y that it can't be 0 in this constraint set. So what we additionally have to add is so-called linking constraints, which tell us that xij is less than or equal to some big M multiplied with yij. So if yij is 1, then xij can take an arbitrarily high value. But if yij is 0, then the entire right-hand side of this constraint is 0, which means that xij also has to be 0. So let's look into the right big M, because big M right now can, of course, be a lot of different values. So first of all, the optimal big M, of course, does not cut off any optimal solution. Secondly, the right big M is as small as possible. And that has computational reasons. Otherwise, it's just going to take us very long to solve this problem using Gurobi or any other off-the-shelf solver. And in this particular case, it's the minimum of supply at the source and demand at the sink. So if we have 3 bikes parked here and we have a demand of 2 bikes over here, we would never move more than 2 bikes between them. Of course, if we have a demand of 4 while we're having a supply of 3, we might not move anything more than 3. So M is the minimum of OI and DJ for all I and O and J and D. Now, what I would like you to take away from this web lecture on the fixed charge transport problem is, first of all, what the fixed charge transportation problem is. Secondly, the wrong model. Then the linking constraints. And lastly, the big M. So both what the big M is and how we're setting it in this example. Thanks.